in this question we are to find all solutions to the ordinary differential equation. So we have y prime is equal to t squared plus y squared, all divided by ty. Now, looking at this differential equation, you could see that each term has a degree of 2. This is 2, this is 2. Here the t is to the power 1, the y is to the power 1. If I add the 2, it's also 2. Therefore, I can say that this is homogeneous of degree 2. So the degree is going to be 2. Now that we know that it is homogeneous of degree 2, the rule says that in solving Euler homogeneous differential equation, we have to multiply the numerator by 1 over t to the power k, where we know k to be 2. Then we also do the same thing for the denominator, 1 over t squared. Now let's multiply 2. If I multiply 2, I'll get y prime is equal to 1 plus y squared t squared, which is y on t, all squared, y on t all squared, then all divided by t will cancel t, then I'll be left with y on t, y on t. So this is what I have. The next thing is to make a substitution that lets u be equal to y on t. Then I can make y the subject, y is equal to ut. Then I can find y prime. Y prime is equal to, if you differentiate u, you get u prime. You hold u and differentiate. Now let me start. Hold u and differentiate t, so you get u plus hold t and differentiate u, you get u prime multiplied by t. So that is my y prime here. I can substitute it here, so it's going to be, wherever I see y prime, I'll write u over u prime t should be equal to 1 plus y on t is u, so u squared, all divided by u. So let me write it down again. From here, I need to bring this u to the right hand side. So I have u prime t should be equal to 1 plus u squared all over u, then minus u. Let us continue. I have u prime t should be equal to, I can make u the our LCM is u. So I have 1 plus u squared minus u squared. Then I finally have u prime of t should be equal to 1 over u. Multiply through by u. I have u prime multiplied by u multiplied by t should be equal to 1. Then divide through by t. I have u prime of u should be equal to 1 on t. Now when you get to this point, u prime is the same as, let me write the u first. U prime is the same as du dt should be equal to 1 on t. So multiplying through by dt, I have u du should be equal to 1 over t dt. So we can clearly see that this is a separable form. All the u's are to the left hand side and the t's are to the right hand side. So we can go ahead and differentiate this. When we differentiate u divided, I'll get u squared over 2. If I differentiate u, I'll get u squared over 2. No, sorry, I am integrating. So if I integrate u divided u du, I'll get u squared over 2 should be equal to, if I integrate this, I'll get the natural logarithm of t plus our arbitrary constant. Let's say the constant here is c1. Now I can multiply through by 2. If I multiply through by 2, I'll get, well, so when I get to this point, before I multiply through by 2, let's look at the substitution. We know that u is equal to this. So let's substitute it inside. I'll get u squared. U squared is equal to y on t all squared over 2 should be equal to ln t plus c1. That's the constant. So from here I can multiply through by 2. I have y squared over y squared over t squared should be equal to 2 ln t plus 2c1. Then from here I can still simplify. Now if I square root both sides, so if you like, you even maintain y over t squared here. When you square root both sides, you will bring plus or minus here. So I have y on t should be equal to plus or minus square root of 2 ln t plus 2c1, but 2c1 is still a constant, so I can say c. Then the final thing is to make y the subject. Y is a function of t, which is equal to plus or minus the square root of 2 ln t plus c. Then remember I'm multiplying through by t, so the t will come here to multiply. So let me put it this way. plus or minus t root of ln t plus c, and that is the solution.